This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on differentials. So we have these two notations for a derivative. F prime of x is a derivative. The derivative of y with respect to x is a derivative. So each of these notations means essentially the same thing, but we're going to use this notation to help us come up with this notion of a differential. So in essence, we're multiplying both sides by dx. That's a little bit of an abusive notation, but it helps us get to where we're getting. So dy represents a change in y, dx represents a change in x at an instant. But the reality is the change in x is usually some kind of a number, so we're dealing with a secant rather than a tangent. But if the change in x is very small relative to the function, then we can say the change in y is approximately the derivative at x times the change in x. This is the basic idea behind the differential, in that dy dx is similar to change in y over change in x. In fact, dy dx is the limit as change in x goes to 0 of change in y over change in x. So as long as change in x is relatively small, this is a pretty good approximation for the change in y. So let's go through the process. If I have f of x is x squared plus 3x plus 5, x is 1, and dx is 0.04, so this will be an instantaneous change. We want to find dy. So we're going to use the fact that dy dx is f prime of x. So we know dy dx is 2x plus 3. So if that's the case, dy would be 2x plus 3 times dx, again, mentally thinking of multiplying both sides by dx. Well, we know dx is 0.04, and we know that x is 1, so just making that substitution, we can go ahead and see that dy is 2 times 1 plus 3 times 0.04, or dy is 0.2. So that's the idea behind the differential, but we actually use it to approximate functions. So using the same problem, we're just going to think about it a little differently. So I've got f of x is x squared plus 3x plus 5. I want to use a differential to approximate f of 1.04. Now, of course, you could plug 1.04 in for x and get the actual answer instead of an approximate answer. But this is a nice technique that shows you how changing one variable changes the entire function and to what degree that happens. So the differential is indeed a very nice application in mathematics. So what do we start with here? Our original x is 1 because 1.04 is very close to 1. And I could plug 1 in for x. 1 squared plus 3 times 1 plus 5 would give me my original y. So my original y is f of 1, which of course is 9. So my answer f of 1.04 is probably going to be somewhere near 9. So I've got to find my change in y. So I'm told the change in x is 0.04, so that's going to behave like dx. I want to find change in y, which is going to behave like dy. So how does that work? So here's the bits that we have. Again, x is 1 from 1.04, y is 9, plugging 1 in for f. Change in x is 0.04 because 1.04 is 0.04 more than 1. We use our idea that dy dx is f prime of x. So dy is f prime of x dx. Now what am I going to use for x? I'm going to use 1, but I've got to take the derivative of this function. So f of x is x squared plus 3x plus 5. F prime of x is 2x plus 3. But again, our notion is going to be that the change in y is approximately f prime of x times the change in x, because dx is approximately change in x as long as the change in x is small. And then in that case, dy would be approximately change in y. So we're going to say change in y is approximately f prime of 1 times the change in x, which is 0.004. Again, f of x is x squared plus 3x plus 5. The derivative is 2x plus 3. If I plug 1 into that, we get 2 times 1 plus 3. That part would be 5 times 0.04. And the change in y, as we saw in our first question, is still 0.2. But our original y was 9, and our change in y is 0.2. So that gives me an approximation for f of 1.04. So f of x plus change in x, so f of the original x plus the change in x, should be approximately the original y plus the change in y. My original x is 1, my change in x is 0.04, so that's f of 1 plus 0.04. My original y is 9, my change in y that we approximated is 0.2. So I believe that f of 1.04 should be approximately 9.2, using a differential. But we could find the actual number just by plugging 1.04 into this function. If I took 1.04 squared plus 3 times 1.04 plus 5, I should get something close to 9.2. Did we? 9.2016. I'd say that's pretty close to 9.2. So this is an approximate answer. This is an actual answer. The 9.2 is what we get from the differential, and that indeed what this question was asking, was to use that differential to find that approximate value. Here's another standard example. We want to use a differential to approximate square root of 9.01. So we know the square root of 9 is 3, so my original x is going to be 9. My change in x then would be 0.01. My original 9, if my original x is 9, my original y would be square root of 9, or 3. And then my change in x is 0.01 because I'm 0.01 away from 9. So I want to use all that information to find the change in y. We're going to use our differential to say f prime of x is dy dx, and then go through the analysis there. So dy dx is f prime of x, so dy is f prime of x dx, or change in y is approximately f prime of x times the change in x. Change in y is what I want to find out. So the x I have is 9, I need to have f prime, that's one thing I'm going to need to have. Change in x is 0.01, we have that. So let's see where we go next. So the change in y is approximately f prime of 9 times 0.01. Of course, x is 9, change in x is 0.01. But now how about my derivative? How about my f prime of x? Well, f prime of x is the derivative of x to the 1/2, which is 1/2 x to the 1/2 minus 1, 1/2 x to the negative 1/2, which is 1/2 times 1 over root x, or 1 over 2 root x. I'm going to plug 9 in for x. F prime of 9 is 1 over 2 times the square root of 9. That would be 1 over 2 times 3, or a sixth. So 1/6 times 0.01 gives me 0.001667. That is my approximation for the change in y. My original y was 3. Based on this, I'm saying my change in y should be going up by 0.001667. That will give me my approximate value for the square root of 9.01. So there's all the information we have. F of x plus delta x should be approximately y plus delta y. X, 9 plus 0.01. And then our function, of course, is the square root of x. Our original y is 3. Our change in y is 0.001667. So we predict that the square root of 9.01 is approximately 3.001667. But again, I can find the actual number. All I've got to do is ask a calculator for the square root of 9.01. And I get 3.00166662. And you can see our approximation here is a very good approximation for the actual number. Okay, moving to an application. A company manufactures and sells X transistor radios per week. The weekly revenue function is given by this. We want to use a differential to approximate the change in revenue if production is increased from 2,000 to 2,010 units per week. So we have our function r. Our original x is 2,000 and our change in x is 10. Our original r is going to take some work. We're going to have to plug in 2,000 into that function. But then we're going to have to find change in r. Change in r is what we're going to want. Again, original x is 2,000, change in x is 10. Find dr dx, which will give us the change in r eventually. So here's what we start with. Our original x is 2,000. Our original r requires me to plug 2,000 into this function. 10 times 2,000 minus 2,000 squared over 1,000. So my original r is 16,000. So I have my original x, I have my change in x, I have original r. I'm going to need my change in r to get my approximation for the revenue when x is 2010. That's what we're going to want to find. How are we going to do it? Well, the derivative of r prime of x, should be dr dx. So we're going to need to at some point get that. So let's take a look at what r prime of x is. The derivative of the first piece minus the derivative of the second piece. Pull the constant out in front. 10 times the derivative with respect to x. Pull the 1 over 1,000 out in front. Minus 1 over 1,000 d dx x squared. The derivative with respect to x of x is just 1. The derivative with respect to x of x squared is 2x. 10 times 1 is 10. 2x over 1,000 is x over 500. So I have r prime of x is 10 minus x over 500. I'm going to need r prime of x to find change in r, since r prime of x will be equal to dr dx, approximately change in r over change in x. So here's all the information we have. Let's find out what r prime of 2,000 is, because we're going to need that in our problem. So plugging 2,000 in for x, 10 minus 2,000 over 5,000 would be 10 minus 4, or 6. So r prime of 2,000 is 6. I will need that in my differential. So r prime of x is dr dx. So r prime of x times dx is dr, where r prime of x times the change in x is approximately, that should be an approximately sign, change in r. So x is 2,000, r prime of 2,000, times the change in x is 10, should be approximately the change in r. R prime of 2,000 was 6. 6 times 10 should be approximately the change in r. So 60 is approximately the change in r. We started with 16,000. Our change in r is 60, so our new r will be 16,000 plus 60. So r of x plus change in x should be approximately r plus change in r. X, 2,000, change in x, 10. So r of 2,010 should be approximately 16,000 plus 60, or 16,060. But I can also find out what the actual number is just plugging 2010 into this and doing the computation, and we get 16,059.90. So just a 10-cent difference between our predicted answer using the differential and the actual answer looking at the function. And that will conclude this lesson.